Hello, my name is Roland. This is a presentation of our paper towards general and autonomous learning of core skills, a case study in locomotion. Our long-term research goal is an agent architecture with a high level of autonomy, as it can learn from minimal prior knowledge, working directly on raw input and actions, that is data efficient enough to work on real robots, and general to work out of the box on a large set of tasks and domains. Or in other words, our long-term research question is, can we define agents that work across a large set of domains and tasks without requiring tedious engineering and fine-tuning? Our main approach follows the idea that we already described in the simple sensor intentions paper. There, we showed that using up-to-date multitask off-policy reinforcement learning methods, like the scattered auxiliary control, can be used to learn complex tasks only from a set of very simple auxiliaries. In this paper, the main question was how powerful these methods can be and what we can gain from them in the domain of locomotion. In particularly, we asked the challenging question if we can find simple and versatile rewards in locomotion that are general enough to generate diverse locomotion behaviors over a broad range of different locomotion creatures. And if using our methods and a single agent can act as a general locomotion module that successfully learns on a wide range of creatures. While we ground our experiments on a platform that follows a modular approach in hardware, the Heavy Robotics DAISY platform, we also build a modular simulation that allows us to perform a large number of experiments on a large set of very different robots in simulation. Overall, we have a zoo of 9 different simulated platforms with very different kinematics and dynamics properties, ranging from 3 to 6 legs with arms or even wheels. In this paper, we investigate a set of 8 different core reward skill definitions that follow the same principle. They are only based on rich onboard sensory information of the robot, are based on simple principles, and use the same reward schemes for all robots. Using these skills in combination with a powerful off-policy reinforcement learning method enables the robot in principle to learn anywhere, independent of dedicated lab settings and platform-specific, highly human-engineered shaping rewards. A good example of how powerful these simple rewards are is the walk forward skill. It is a simple combination of a reward to keep the torso level using the IMU orientation estimates, while roughly speaking, giving reward for moving some reference points defined on the robot forward relative to each other. Nevertheless, we can learn a very symmetric and efficient gait for the DAISY hexapod from scratch and only using onboard sensors just by interaction with a pure interaction time that is less than 60 minutes. Also being very simple and only based on onboard sensors of the robot, we were able to show that the same reward scheme worked for the same agent with the same hyperparameters over different locomotion creatures with very different kinematic and dynamic properties. For example, we can not only learn a gait for the hexapod, but also for all different quadrupeds and even a 3-legged robot. And it even can generate a very good gait for the bipeds, where the task is clearly much more challenging. Especially interesting is that these skills produce very diverse and interesting locomotion behaviors, using the same agent and principles. For example, the agent can make use of the robot arms without it being explicitly specified in the reward. Still, we can learn all skills from scratch in less than 7 hours. This was especially striking in true robustness ablations, where the same simple rewards showed that they can also overcome obstacles and even work when you put passive skate under the feet, and that they can get very creative. As we saw, the simple rewards can generate a very versatile and diverse set of locomotion behaviors over a large set of different robots. If you combine them now with a simple sensor intentions idea, we can learn a versatile locomotion module. This locomotion module does not only learn a set of skills, it also learns skills that are more versatile, as they learn every possible transition between each other without falling. The most important point of our approach is that this locomotion model can make use of these versatile core skills to solve more complex skills, where learning from scratch would completely fail otherwise. And besides the versatility, using this locomotion module makes learning also more data efficient. Finally, we showed that we can reproduce the most important walking experiment on a quadruped DAISY using the same agent, hyperparameters and reward schemes we used in simulation, learning an instance of a locomotion module on a real robot. As the results are matching quantitatively and qualitatively pretty nicely for this platform, we can have high hopes that the other results we achieved in simulation will also be meaningful for the real world. As a conclusion, in this work we showed that we can learn diverse locomotion skills from scratch and only based on onboard sensors with the same agent, hyperparameters and reward schemes over a set of 9 different simulated and 1 real robot. Especially by using a multitask reinforcement learning approach, we can learn for all of the platforms a versatile locomotion module in a very data-efficient way that is able to solve complex tasks and learns to walk on a real quadruped robot in only 40 minutes of interaction. Thanks.